Good day, class. In today's video, I will introduce the Jacobian Matrix. So this is an important tool in robotics. This is the matrix that relates the end effector velocities to joint velocities. In other books, this is the partial derivatives of the forward kinematics equation. So in physics and in calculus, we have different types of velocity. So we have the constant velocity, which is the displacement over time, the average velocity, which is the change in displacement over change in time, and instantaneous velocity, the rate of change in displacement with respect to time. So these are the formula of each velocity. Okay, so in this topic, we will use instantaneous velocity. Okay, so let's establish the type of velocities we need in the study of Jacobian matrix. Okay, so again, instantaneous velocity is the differential of displacement with respect to time. We have two types of velocity, the angular velocity and the linear velocity. So angular velocity is from the angular displacement due to rotation. Okay, so its differential is the angular velocity. Okay, we will write it as a theta prime. Next is linear velocity. Okay, it's from the linear displacement. Its differential is the linear velocity. So these are our linear velocities: the x prime, the y prime, the z prime, and the d prime. Okay, so this is the form of Jacobian matrix. Okay, this is the form of Jacobian matrix. So uh, founded by this is founded by Carl Gustav Jacobi in 19th century. Okay, so this is the general formula of Jacobian matrix. The J inside is the Jacobian matrix. This vector is the end effector velocity vector, and this right vector is the joint velocity vector. So this end effector velocity vector is composed of the three linear velocities of end effector, okay, the x prime, y prime, z prime, okay, which is the velocities of end effector at x, y, and z direction, while the omega x, omega y, omega z are the angular velocities of end effector at x, y, and z axis. The joint velocity vector is composed of the joint variables of the mechanical manipulator, but they are in differential form. Okay, so these are the theta n prime or the dn prime. So to start, we need first to know the dimension of our Jacobian or Jacobian matrix. So our Jacobian or Jacobian matrix composed of rows and columns. So the number of rows depends on the number of rows of the end effector velocity vector. So the rows of the end effector velocity vector is always 6, while the columns of our Jacobian matrix is equals to the number of rows in the H parametric table. So if our number of rows in the H parametric table is 3, the number of columns of our Jacobian matrix is also 3. While the joint velocity vector, the number of rows of the joint velocity vector will depends on the number of the columns of the Jacobian matrix, and it will hold, or it will be composed of either theta n prime or dn prime. Okay, so this is our example, a, a Cartesian manipulator without a stand. Okay, the Jacobian, the size of the dimension of the Jacobian matrix for this example is 6 by 3. Okay, why 6 by 3? Is because we have 6 rows at our end effector velocity vector and 3 rows of parametric table for this uh, Cartesian manipulator. So the number of rows of our parametric table is equal to the number of frames minus 1. So we have 4 frames, so minus 1, so 3 rows. Okay, so our columns are 3. Then our joint velocity vector is also 3, which is from the number of the columns of our Jacobian matrix. And it will compose of uh, the joint variables of our Cartesian manipulator, the D1, D2, and D3. Okay. So after after knowing the dimension of our Jacobian matrix, we will solve for the elements of our Jacobian matrix. So to solve for the elements of the Jacobian matrix, we need to use the linear algebra method. Okay. There are different method of solving the Jacobian matrix. These are the partial derivative method, the partial derivative of the forward kinematics, and the propagation method. Okay? But we will use the more accurate method, which is the linear algebra method, which use linear algebra to solve for the partial derivative of each element of our uh, Jacobian matrix, and also because this is a 6 by 3 6 by 3 Jacobian matrix. Partial derivative method is only used if the Jacobian matrix is composed of 2 by 2 dimension. Okay, so this is the formula that we will be using our linear algebra method. So it composed of the linear rows and the rotational rows. In linear rows, we need to identify if the column is a prismatic or revolute. If it is prismatic, we will use the prismatic formula. If it is revolute, we will use the revolute. The same with the rotational rows. If it is prismatic, this will be used as the vector of the first column for for the rotational row. If it's revolute, we will use this. So in our example, all of the columns are prismatic, so we will use the formula of prismatic joint. Okay. So additional information in our linear algebra method, the R stands for rotation matrix, which must follow the superscripts and subscripts. The D is the position vectors, which will need to follow the superscript and subscripts. I is the joint or column you are solving, while N is the number of joints or columns of the Jacobian or Jacobian matrix. Okay? So in our example, the working equation will be look like this. Will look like this. Okay. So in our first column. Okay, so this is the R00 rotation matrix times 001 vector and 000 vector. Then in our second column, the R01 rotation matrix times the 001 vector. Then the 000 vector. And lastly, the R0 to rotation matrix times the 001 vector and 000 vector. So this will be much easier because our rotational rows are in zeros. Okay, so to solve this, okay, we need to find the rotation matrices, okay, for each column. So we can obtain the rotation matrices using the program of, of the forward kinematics, then extract the rotation matrices from the homogeneous transformation matrices. But for now, I will give the the value of R01 and R02. R00 means the projection and the the reference is in 0. So our rotation matrix here is a or is an identity matrix. Okay. So this is our identity matrix times the 001 vector. So so uh, any 3 by 3 matrix that you will multiply to a 001 vector, the answer is the third column of that 3 by 3 matrix. Okay, so this is our first vector. Next, R01. Yeah, so I will give the rotation matrix R01. So here it is. So again, any any 3 by 3 matrix that will be multiplied to a 001 vector, the answer is the third column of the 3 by 3 matrix. Okay. Next, R12. So to solve, R02. To solve R02, we need to know what is R12. Okay. We need to know what is R12 so that we can solve for R02. So because we will multiply R01 to R12. So we will have here a 3 by 3 rotation matrices multiplication. Okay, so this is the answer. This is the R02. Then multiply R02 to 001 vector. Okay, so this is the R02 times 001 vector. So this is the vector we need for the okay, for the for us to obtain the Jacobian matrix. Okay, so we will put our vectors in our Jacobian matrix. Okay, so we will put the 001 here. We will put 001 here. Then 100 here. Oops. Okay, why is that? Again. Let's put 100 there. Then lastly, R02. Okay. So this is the Jacobian matrix of our Cartesian manipulator, but this is not the final answer. The final answer for this is our differential equations. We need six differential equations. These differential equations are the velocity equations of the Cartesian manipulator. So what we will do here is we will multiply the 3 by 3 matrix to our 3 by 1 joint velocity vector, then obtain the differential equations by equating them to our end effector velocity vector. So this will be the differential equations. And if we simplify it, okay, so this is our differential equations. If we notice, omega x, omega y, and omega z are all equals to 0 because the Cartesian manipulator has no rotational movement or no revolute joint. So just have x prime, y prime, and z prime differential equations. Okay. So how to interpret the differential equations of the Jacobian matrix? Okay. So the differential equations of from the Jacobian matrix is used to interpret or to analyze the the velocity of the end effector and joints of our mechanical manipulator. Using these differential equations, we can identify how to uh, how to change the velocity or adjust the velocity of our end effector in the x, y, and z axis, as well as the rotation along x, y, and z axis. So in these differential equations, in these three differential equations, to make the end effector faster at the x direction, okay, at the x direction, we need to adjust the velocity at the uh, d2 prime or at the joint or at the joint variable d2. Okay? Based on our kinematic diagram, d2 is along the x sub 0 axis. So it matches the differential equations we obtained from the Jacobian matrix or Jacobian matrix. Next, if we want to get it faster at the direction of y-axis, we need to adjust at the joint variable d3. Okay, so the negative sign here shows that the end effector is going downward. So d3 is the joint variable pointing downward, so that's why it is negative. Next is z03. Sorry, z prime. So to make the end effector faster at the z-axis, okay, we need to adjust the value or the velocity of the joint variable d1. Okay, so this is the application of the differential equations from the Jacobian matrix. So this is from manipulator which uh, joints are in prismatic, are all prismatic. So what about mechanical manipulator with revolute joints. So in our example 2, we have here a 2 degree of freedom articulated manipulator. So it has two joint variables and two moving links. Okay. So the dimension of the Jacobian matrix is 6 by 2. Then all the columns are revolute joints. So we will use the formula of the revolute joint. So our working formula or our working equation be look will looks like this. Okay. Okay. So we have now here the difference of two position vectors. So we will solve first the first column. So at the first column, we have here the rotation matrix R00 times the 0, 0, 1 vector. Okay. So again, the R00 rotation matrix is just an identity matrix. Okay. So the answer here is the third column of the identity matrix. Next, the difference of D02 and D00. So D02, this is the given D02 and this is the value of the D00 vector. So D00 vector is just a vector where where the elements are all zero because there is no change in position. Okay, that's why the the elements of our position vector are all zero. So the difference of D02 and D00 is this. Then what we will do next is we will multiply the answers, the vector answers with each other. So before that, let's solve for the second column. So the second column is the rotation matrix R01 times the 0, 0, 1 vector times the difference of D02 minus D01. Okay, so this is the R01 times the 0, 0, 1 vector. Then the position vectors, D02 and D01. So this is the product and this is the difference. Okay, so we will put it in our Jacobian matrix like this. Okay, so based in the rules of uh, vector multiplication, we cannot multiply a 3 by 1 to a 3 by 1 vector. So this they are both 3 by 1. Oops, sorry. So this is also 3 by 1. This is also 3 by 1. So because we cannot multiply two 3 by 1 vectors, what we will do is we will use the cross product formula. So in the cross product formula, we have the vector A and the vector B. Okay, using the cross product formula, we can combine the two vectors. So in this given, so this first one is the vector A, then the second one is the vector B. Okay. So let's use the cross product formula with each vectors. So for the first vector or for the first column, this is the two vectors. So the answer here is this. Okay. So we just use the the cross product. Okay, the cross product formula. For the second column, this is our vectors. And this is our vectors. So the answer here is this. Okay, we have a trigonometric identity at the third row. Okay, so we will put it in our working equation or in our Jacobian matrix. So this is our Jacobian matrix. So like the Cartesian manipulator, we will obtain the differential equations by multiplying the 6 by 2 matrix to the 2 by 1 joint velocity vector. Okay, so this is the differential equation. Okay, from this Jacobian matrix form or the Jacobian matrix formula. Okay, so these differential equations will be used to analyze how will we change the velocity of each joint of the mechanical manipulator. Okay, uh, we have a complete six differential equations. Okay, so this is the Jacobian matrix. So we will use this to analyze the velocity of our mechanical manipulator as well as program it. Okay.